So starting from your initial responses, when you're describing to somebody, a novice, right, what it means for a function to be continuous. What were some of the things that you wrote here? Yeah.
There are no holes or jumps in the graph of the function.
Okay.
So that you could like trace it with your pencil and not pick it up.
Okay. This is a classic form of the definition. No holes or jumps in the graph. So this is a graphical description. You can draw it without lifting your pencil. And that's a good description, I think, for somebody taking pre-calculus, because they know a lot about graphs and when you take a pre-calculus class. And so the idea that you can draw the graph of this function without ever lifting your pencil, that's a pretty vivid illustration. Okay, what else came up in your descriptions? So you're thinking about an analytical definition. Every x has a value in the interval a, b. Can you say a little bit more about what you mean there? So there's one way of reading this statement just as a definition of a function, right? A definition of a function is that every input has a unique output. So what's special about the interval a, b that's going to make this reflect on continuity somehow? So the idea here is that it's not possible for a continuous function to skip over any values from A to B. And depending on what the domain of this function is, remember the domain is all of the x's for which a function is defined. Depending on what the domain is, it may be okay to have gaps in the domain of a function, but the idea for a continuous function is we probably don't want there to be gaps in the range. So one of the ways of getting at what it means for a function to be continuous is thinking about an interval of y values from A to B, and saying that if I have a function where at one value, let's call it x1, it takes the value a, and if at another value, x2, it takes the value b, so f of x2 is equal to b, f of x1 is equal to a. One of the ideas behind a continuous function is that if I draw the graph in between those two points, that this graph is not going to skip over any of the values, any of the y values, between a and b. This is actually a theorem that you pick up in calculus. Anyone remember what this theorem is named? This theorem that guarantees that there exists a c in the interval. Now, how do I want to say this? Let me write this as y here instead of c. There exists a c between x1 and x2 such that f of c is equal to y, and that this is true for any y in between f of x1 and f of x2. Anyone remember the name of this theorem? Theorem that says that for any value in between two values of a continuous function, there has to be a way to make the function take that value. We can't skip over any y's. If I add one more word in front of this theorem, there's just one more word in front of this one. This is the intermediate value theorem. So one of the ways of describing what a continuous function is by describing what it does. What it does is it doesn't miss any of the values in between any two values that it takes. Right? That's another way of kind of being really specific about this no holes, no jumps kind of idea. Right? That for a continuous function, when I take any two values, a and b, I also must take all the values in between, right? As long as my function is defined on this entire interval from x1 to x2. So based on the definitions that you first wrote down as an attempt to explain to somebody in pre-calculus about what a continuous function is, what were some of the rebuttals? What were the, how do you know x? What are the what if x? What were your okay buts? Either the ones that you wrote or the ones that were written to you. Is that another way to say how do you know on which interval a function is continuous? And how did you respond to that? So what I'm feeling is that we have a ways to go as a room here, understanding what is it that makes a continuous function continuous. And both of these two initial stabs here are getting at one piece of the puzzle, right? It's like the old parable about the people in a dark room, each feeling one part of an elephant, right? Like, I'm feeling the elephant's leg and say, oh, this is a tree. You're feeling the trunk of the elephant and say, oh, this is a snake, right? And then turn the lights on and you find out, oh, it's just an elephant. We're all feeling the same thing. Same thing about continuity, right? Each of these aspects is one aspect of the definition of what makes a continuous function continuous. But what we want to know is what's the whole elephant of this definition? What is it that's going to make a continuous function continuous? What does it have to do with calculus? And then based on what it has to do with calculus, what does then it have to do with us in real analysis? So supposing for the moment, just to make our pivot here, where we're going to end up today, now suppose that instead of describing this idea to somebody taking pre-calculus, how does it connect into calculus? What's the connection in calculus that tells us when a function is continuous? What's the concept that we need in order to make that definition precise? Calculus, in a very real sense, calculus is the study of limits. It's what makes it different than pre-calculus and algebra and everything that came before it, is that we study the limit of a function. And that is the definition, that's the concept that powers our notion of continuity. It's the concept that powers our definition of the derivative. It powers our definition of the Riemann integral when you do it in the second half of calculus. Limits are everything when it comes to calculus. And now that we've taken 6 weeks, longer, to slog through sequences, I think we've earned now, finally, the right to leave sequences behind for a while and replace sequences as our object of study with functions, something more familiar, something that we can draw graphs of, something that we feel like we understand the properties of better, having come through calculus. All of the analytical mathematical disciplines like calculus and differential equations and so forth, all of those have to do with functions of a real variable. So those are going to be our objects of study. When we define the limit of a function, that's the concept that's going to let us get at what it means for a function to be continuous. So just to wrap up, let's recall how it is that that definition plugs in. In order for f, a function f, to be continuous at a point, let's call it x equals a, the point we want it to be continuous at. Does anyone remember what is it that has to be true? How do limits plug into this idea? So if this blue dot on my graph has the x value a, so this is the point at which I would like to justify why this function is continuous, then the y value is f of a. Why is it that I know that this function is continuous? What can I say about its limit near x equals a? Okay, so those two things are both aspects that need to be true in order for this limit to exist in the first place. So the first thing we need is we need the limit from the left of this function to be equal to the limit from the right of this function. And those two things together will guarantee that this limit from both sides of f of x exists. We can see on the graph that the limit exists because this is the game that we play in calculus. The closer that our x values get to the value a, the closer that the y values get to the value f of a. And that's true from the left, it's true from the right, and both of those tell the same story. Therefore, this limit exists. But so far, there's nothing in our definition that says anything about whether there might be a jump in the graph at this point. Maybe this is actually a hole, and maybe the function value at that point is actually up here. So how do we prevent this from happening if we want our function to be continuous? What's the one more thing that I need? I don't just need the limit to exist. I need to be equal to what? I need to be equal to f of a, right? And that prevents there from being a jump. So here the limit exists, but the function's not continuous because the value at that point doesn't agree with the limit near that point. So in order to get our definition of continuity that we like from calculus, we need the limit to exist, and we need it to be equal to the value. When I teach calculus, I usually describe this as saying that the nearby story of this function has to agree with the at story. Right? The value the function takes near x equals a has to agree with the value that it takes at x equals a. And that's what it means for a function to be continuous at a point. And so in order to get there in analysis, we have to understand what goes into the definition of that limit. How do we actually define what a limit is? And try to get away from using words like as we get closer and closer and infinitely close and so forth, all that vernacular that you used for sequences for a while in calculus. How do we put this onto a similarly firm foundation? And then how do we also tie this question of continuity back to the properties of the real numbers that we've been studying this semester? What property of the real numbers lets us not lift our pencil when we draw the graph of a continuous function, for example? So those are the connections that we have to start to build out.